So let's talk about the confidence intervals for an equal and unequal variance t-test. So remember, what are we trying to consider here? We are trying to consider, when it comes to these two populations, their difference in mean, that equals some value. Now it's usually going to be 0, but it need not be 0. Usually under the null hypothesis, we're going to say that those two are 0, but we don't know these two values. So at best, we're going to just take a couple of people from our population, and we're going to have that difference between those two sample means. But we want to construct an interval around this difference, and we want to express some level of confidence that this difference lies within this interval here. So here I have some approximation. Is definitely not proper and not to scale, but it's the best I can draw of some probability density function of my t-distribution given some degrees of freedom nu. And so it goes off to negative infinity, positive infinity. So what does this horizontal axis mean? Well, it's all the t values. If this was really true, that there is some, let's just say that they're equal to each other. I have these two populations and I randomly sample from each one of those, calculate a t value and do this over and over and over and over again. I'm going to get a bunch of t values. Just at random, there's going to be a bit of variability. And we're saying that under certain assumptions, and specifically under the null hypothesis, if those two are equal, this is going to be, so we can put a 0 there, this is going to be the probability density function, this distribution of all possible t values that I might find. If I have some interval here in the middle, that's where I'm going to find, that's a big density there, and I'll find most of my values here, and then out here in the tails, I'll find less. And I can decide, which are the common ones that I want. What level of confidence do I want to express? And we'll usually say that's 1 minus alpha. So if we choose our level of significance to be 0.05, 1 minus 0.05 is 0.95. So this interval of values would contain 95% of all the t values if I were to do my study over and over and over again. Great. So what are we saying to each other? We want to say, well, where between these two values of c, and I'm going to say c, we use c for confidence coefficient, when we use the z distribution. Actually it's t subscript nu comma alpha divided by 2, but that takes too long to write, so I'm just going to keep on c. I'm saying, for what values of c would I capture the 95% most probable values? So let's write that in statistical notation. I'm going to say the probability that this t value is between these two values. If it's between these two values, the probability that t lands up there, well, that is going to be equal to 1 minus alpha. Whatever I decide my alpha to be, think about the hypothesis testing. If alpha is 0.05, so that's 2.5%, 2.5% of my area under the curve on both sides. So what I've just said in words, that's our statistical notation. I just have to remember how to calculate t. Now there are two of these t-tests, equal and unequal variance t-tests. So let's just write it very generically. We're going to say t equals x bar 1, mean of my first group, minus mean of my second group as far as the samples are concerned, minus this difference in means for the population. Now usually, as we said, we'll say under the null hypothesis that is 0. And we're going to divide that by some standard error. We're thinking about this difference per units of standard error. Now we're going to calculate standard error differently, whether we choose an equal or unequal variance t-test. So let's just keep it generic there as the standard error. So let's think about this. I now have an equation for t which I can plug in here. So I'm going to say the probability from negative c less than or equal to x bar 1 minus x bar 2, that difference in those sample means, minus mu sub 1 minus mu sub 2 is less than or equal to c. Now remember, I don't put c, I've got to actually put all of that. Well, the probability that t lands between these two is going to be 1 minus alpha. And if I choose a different alpha, my confidence level changes. So these two change. Okay, now I have to remember that I have to divide all of this by the standard error. And now it's going to be a lot of algebra that's going to come from this. Now, the standard error is going to be non-negative. So I can multiply throughout. Now do remember, there's an inequality, so it actually should write both of them. But we can do it all in one go. So let's multiply throughout by the standard error. So I'm going to say the probability that minus c times the standard error. I don't have to flip the signs because that's non-negative. And if I now have a numerator, standard error, and a denominator, those are going to cancel out. So here I'm just left with x bar 1 minus x bar 2 minus mu sub 1 minus mu sub 2 less than or equal to c times I multiplied throughout by the standard error, and that's still going to be 1 minus alpha. Now what I can do is I can subtract this x bar 1 minus x bar 2 from both sides. And so if I add to that negative this, it'll disappear from this term. So let's do that. I want to give myself a bit more space. I'm going to say minus x bar 1 minus x bar 2 minus c times the standard error. That's less than or equal to. Now I've got negative that difference plus that difference, so those cancel, and I'm left with minus mu sub 1 minus mu sub 2 is less than or equal to, and now I've got negative x bar 1 minus x bar 2 plus c times the standard error is equal to 1 minus alpha. So that's great, but what I want to do now is I'd like to get a positive here, so I'm going to multiply throughout by negative 1. If I multiply throughout by negative 1, of course, these signs have got to flip. So I'm going to say p is less than or equal to, now a negative times a negative is a positive, so that's going to be a positive x bar 1 minus x bar 2. That's going to become a positive as well, c times the standard error. Now the sign flips, larger than or equal to. Here I'll have mu 1 minus mu 2. Now that sign flips as well, greater than or equal to. Negative times a negative is a positive. So that's x bar 1 minus x bar 2. And that negative times a positive becomes a negative, c times the standard error. And that's still going to be some level of confidence. Now I just want to rewrite this. And so I'm just going to flip everything around. So I'm going to say the probability, so I'll still have mu sub 1 minus mu sub 2 in the middle. But now I see mu sub 1 minus mu sub 2 is greater than or equal to this bit. So if I write it on this side, it's greater than, or if I read it from this way, greater than or equal to that bit. So let's put that there. X bar 1 minus x bar 2 minus c times the standard error. And if I read this in this direction, so mu sub 1 minus mu sub 2 is less than or equal to this bit, which is x bar 1 minus x bar 2 plus c times the standard error, and that equals 1 minus alpha. And that's exactly what we want. We say, let's build a confidence interval, and there is the equation for my confidence intervals. So let's write that in green, because that is one that we have to keep. We're going to say, well, I'm going to do my study. This is going to be my difference between my two sample means, plus or minus, there's the minus, there's the plus, c times the standard error. And that c, we remember, well, that's exact. If we write it, in more standard notation, that's going to be plus or minus t, some new degrees of freedom, alpha divided by 2 times the standard error. So I want to be so many units of standard error away from above and below this difference in mean. And that's how we get this calculation of the confidence interval around this value. And we are this confident that the true difference there is going to lie on this interval that I'm going to calculate here around this value, around this difference in my sample means. I'm going to create a symmetrical difference, a little interval around those two, such that I'm thinking I'm this confident that this value is in that interval.